Alright, so I got a few requests to start out today, so I'm going to go ahead and respect their time and go ahead and get this started. So I've gotten 2 questions regarding the WebAssigns. Well, 3 questions regarding the WebAssign, but 2 are about the same type of problem. And the first one's going to come from the homework entitled Orders from Concentrations. So I'm going to switch my desktop over to you really quick. So particularly number 2, you get this table of rates and concentrations. So let me just go ahead and transcribe them over on my side. So we've got rates of 0.0633, 0.222, and 0.1785. Concentration of A, 0.122, 0.122, 0.244, and on the B side, 0.224, 0.112, and 0.224. Now these are what are referred to as method of initial rates problems, so MOIR. Method of initial rates, traditionally the way you should do it. Some books try to teach you to do it by inspection. We'll say it's cute. You're rarely given that type of control over the reaction. So the correct way to do these types of problems is first we're going to assume our rate law takes the form R equals K, A to the alpha, B to the beta. Meaning that we're going to assume that we have a power law relationship and that our rate is connected to the concentrations of A and B through some power alpha and beta multiplied by some constant K. Now, if you go through the notes, I worked through the derivation on how to do this, but you can prove that for comparing two rates, you get the relationship the natural log of rate 1 over rate 2 equals the order of A times the natural log of its concentrations between the two rates plus the order on B, natural log the concentration of B between the two runs. Now, a few comments on this. These alpha and betas are what are referred to as apparent orders. They look like they are this order with regard to the concentrations we've seen. Now, why do I emphasize that point? Well, this is an assumption. When you're using method of natural rates, you're assuming a form of the rate law, and because you're making this assumption, you could be wrong. And actually, there are a lot of cases. This is actually the type of problem they like to give senior chemical engineers because it's really obnoxious. How do you prove that your orders are correct? And that's kind of getting into how you actually take the measurements. But at your level, the question is, how do you determine what the order alpha and beta are? How do you determine the apparent orders? Well, if you're a good scientist, what you do is that if you want to understand the effect of one variable, you keep the other one constant. So if we want to understand the order on A, we would pick two runs where the concentration of B are held constant. So we're going to compare run 1 to run 3. And if we look at the concentration of A is doubling its concentration, so we get alpha ln 0.122 over 0.244 equals the natural log of the ratio of these two rates. Now, we can solve for alpha explicitly now, we will get a number. Same thing's true for the order on B, beta. We would compare two runs where the concentration of A is being held constant, but the concentration of B is varying. So this would be run 1 and 2. And we would just use the rate for 1, rate for run 1, rate for run 2, and the concentration of B and 1 and B for 2. What this ends up doing on this side of the equation is the natural log of 1 is 0. So the concentration of A does not change, the ratio of its concentrations is 1, and the natural log of that 1 becomes 0. Now, you will see some books say that the orders have to be integers. That's kind of a misleading statement. What they really should be saying is that for elementary reactions, the rate law based on the elementary reaction must be integer, and that is true. You cannot have fractional probabilities, meaning that the probability of A and B is not going to be some non-integer value. What's misleading about that is almost no reaction written is elementary as written. So to say that the rate law has to be an integer implies that the reaction itself doesn't undergo like other, let's go with putting it, makes a lot of interesting assumptions about the reaction mechanism that are not true. So particularly for number 2, you're going to get the apparent orders for A and B to be 1.5 and 1.7, and that's the point of the problem. To get you out of this mindset, they have to be an integer. They don't have to be an integer because of this assumption. The famous example of this is what's called Michaelis-Menten kinetics. So Michaelis-Menten kinetics, the R here, is K1 concentration of A over 1 plus K2 concentration of A. And with Michaelis-Menten kinetics, if we look at the rate as a function of the concentration of A, for low concentrations of A, it looks first order. But at high concentrations, these two get so big they end up canceling each other out and we get zero order. And between the two, we're going to get an order between 0 and 1. And Michaelis-Menten comes up in biology all the time. So again, don't get locked into this mindset that it has to be an integer. It only has to be an integer if you're deriving a rate law from the actual reaction itself. But if we're taking these measurements, we don't know if it's a rate law. We are making this assumption, and because we are making this assumption, we will inherently find situations where this assumption is wrong and we will get non-integer values because it's not really a rate law and the rate law is trying to fit it like it is. So, other question I got asked. Number 3. So, it's going to be the same line of reasoning. What you're going to get for number 3 for the order of A is 0 order. So what does a 0 order rate law imply? It's possible to get 0 order. So if we look at a rate law, we get R equals K, A to the alpha, B to the beta. And let's say you work out that alpha is 0. So what does that mean when you have a 0 order reaction? Well, it just means the rate doesn't depend on the concentration of A. That's all a 0 order means. Any number raised to the 0 power is 1. So effectively, if the A is 0 order, it means R equals K, concentration of B, to some number. And you can kind of see this in the problem state. You can see this in the data itself. So if you go to the third one, when we vary the concentrations between run 1 and run 2, we don't really see a significant change in the rate. It changes by less than basically 1%. So this would imply then that the concentration of A has no real effect on the rate. And this is kind of backed up by the data. Again, we're changing the concentration, we're dividing it by 3, and the rate barely moves at all. So 0 order is a perfectly acceptable answer. It just means that the rate doesn't depend on the concentration. And we have an example of this. We talked in the graphical analysis. You talk about 0 first and second order. That's a 0 order reaction. The other one. Order from graphs to concentrations, 6C. Let me share my desktop with you really quick. Here we go. So if you've got concentration versus time, then it's a 0 order reaction. So a 0 order reaction is linear if concentration versus time is plotted. The order from there is going to be 0. With all of these graphs, if it's linear, your slope here is going to end up being your rate constant, so 0.0977. Now, it tells you to find the concentration of A, and this is to 3 significant figures. So what you're going to do is do 10.1 for the initial concentration. With concentration versus time, if it's a 0 reaction, the y-intercept here is going to be equal to the starting concentration. So those are the questions I got in terms of emailed questions. In terms of what I'm seeing in the discussion board, there seems to be a misconception about the discussion board that was due yesterday. So a lot of people were giving me the answer that on all 3 graphs the slope equals the rate constant, and they were telling me you had to translate this y-intercept to starting concentration. But there's a contradiction in what you're saying. So there's a reason why the first question is, what is the order of the reaction? So if we have 0 first and second order, And we want to know what concentration versus time looks like. Well, for zero order, A equals the starting concentration minus KT. For first order, it's A equals A naught e to the minus KT. And for second order, 1 over A equals KT plus 1 over the starting concentration. But if you really want to do it as a function of time, concentration of A equals concentration of A naught all over 1 plus KT concentration of A. So the reason it asks you to find the order first is that, let's say we have a zero order reaction, which is what it ended up being. This statement is true. None of these are. This is not true about concentration versus time for a second order reaction. So if you were to take this information, this plot, and put a line through it, you could get a number. And you're going to see this with a lot of the examples. It's very easy to get a number. But that number doesn't have a physical meaning. So if you're looking at a plot of concentration versus time and you say, well, the slope here is related to the rate constant K, but it's a second order reaction, it's not. And the reason it's not is that this is the relationship between concentration and time for a second order reaction. This is not. You cannot fit this to a y equals mx plus b plot. And that's kind of the point. So once you've figured out the order of your reaction, you're going to throw out the two graphs that don't have anything to do with your reaction. Yes, it would be true if you had a zero order reaction that concentration versus time, the slope is going to be the rate constant K. But that's not true for a second order reaction. If you plot concentration versus time for a second order reaction and give it a linear plot, the linear plot is meaningless. It doesn't fit the data at all. The same thing is going to be true for natural log of concentration versus time for a second order reaction. It's meaningless to put a line through it because it's not a line. It's not linear. The only graph that matters is the 1 over concentration versus time data because that should be a line. And we can prove then that that slope of that line is equal to the rate constant K. Yeah, glad that helped. I see a lot of struggle with the transition to Chem 2. You're used to more and this is just more of a comment on transitioning from Chem 1 to Chem 2. Chem 1, I teach, at this point, all levels of chemistry. Chem 1 through Orgo 2 is... Chem 1 is very much like matter of fact. It's like little facts in separation. With Chem 2, it's a lot more synthesis, so we're having to pull a lot more ideas together. So this is typically what I see is that you're more kind of used to like saying, well, this is this, this is this. Particularly with kinetics, for me, it's a nice warm-up to say like, okay, you're having to pull a lot of things together now. You're no longer just stating facts. You're having to assess data. And this is going to be a good setup for when we start talking more and more about equilibrium next and thermodynamics next. It's not just get an answer, it's understanding the concepts and bringing them together. But yeah, you can definitely tell the chemical engineering background, so I have both chemistry and chemical engineering background. Chemical engineers love kinetics. This is going to help you quite a bit to have someone who like really had to like study. What I usually do in class is I bring in my 5 kinetics books. They're about yay thick. Had to work through most of them. There is such beauty in kinetics. I had an excellent kinetics professor when I was in grad school who was the one that explained that a rate law is just 2 probabilities multiplied together, and it makes so much sense when you see it from that point of view. And there's so little you have to like take on someone's word for kinetics. The only thing you have to take my word for in this course for kinetics is that this is the solution for the 0, first, and second order. And that's because we don't require calculus. But if you know calculus and you want to see how to work through it, it's really easy to prove all the reaction order, or all the concentration versus time information for reactions. All right, so those were all the questions I was asked, and this is the only thing I've seen in terms. Oh, actually, one of the questions asked about reactions. So reaction mechanisms identifying intermediates and catalysts. And there were homework questions on this. Good for me. So we'll work the first problem. Oh, nope, sorry. 2 Br radicals. And then 2 H radicals. So the question that was asked was, how do you identify reactions, intermediates, and catalysts? And we'll just talk about these in general. So, best way to think about reactions versus reaction mechanisms is to think about recipes. When you go to make something or when you go to bake something. When you go to the store, you don't write down every step that's involved with making whatever you're making. So the example I give in class is baking bread. That's water, yeast, and flour for a very simple ciabatta. So when you go to the store, the only thing you buy are water, yeast, and flour. You don't care about what gets made along the way. And this is what an overall reaction tells you. The mechanism actually goes through the individual steps. So when you want to make bread, you mix the yeast, water, and flour together, you let it rise, you bake it, and each step in the recipe goes through an intermediate thing. So when you make the dough to begin with, it's unleavened dough. You take the dough and you bake it, or you let it rise, you get leavened dough. When you get the leavened dough, you bake it and you get bread. You have to proceed. You have to make dough to make bread. There's no way around it, but you don't finish with any dough when you're done. The same thing is kind of true with the reaction. Overall, we're taking CH4 and reacting it together to give us the CH3, CH3, and the H2. So this would be the overall reaction. And there are ways to add these together to get to this point, but that's not what really goes on. What really goes on along the way is that we end up generating radicals and intermediates. So the easiest way to identify an intermediate, particularly with the way we try to write mechanisms, is it's first produced as a product and then it's consumed as a reactant. So if we go back to our bread baking analogy, you're going to make dough and then you're going to use the dough. That's an intermediate. We have to make the dough, but we make it so we can make the next step in the recipe. So generally, whatever is produced in your first reaction is probably, those are going to be intermediates. Now, we see each H radical produced, then consumed. We see CH3Br produced, then consumed. We see this compound produced, and then consumed. And we don't see anything else. And so that's what makes them intermediates. We have to make them, but they're immediately consumed afterwards in the next step of reactions. Catalysts are kind of an interesting one in that they are first used as a reactant and then finished as a product. So what happens with catalysts is they are involved in the reaction. Because think about it, if the catalyst was involved in the reaction, how could it possibly speed it up? So it does participate in the reaction basically by changing the mechanism. And that's how we change the activation barriers. But we had to add the catalyst, so it's first a reactant. It gets involved in the reaction, and then it's recovered when we finished. So we would never write it in the overall reaction because it's both a reactant and a product. We would write it over the arrow. But this is more or less how you identify intermediates and catalysts. Go through, see what appears on the right first, and then see what appears on the left, whatever appears on the see what's produced as a product and then immediately consumed as a reactant in a subsequent step. That's your intermediate. You have to produce it to get to the next step in the reaction, but ultimately it's consumed, so there's none of it left over. Catalysts are the reverse. They're going to start as a reactant and they're going to finish as a product. So they're still eliminated from the overall reaction, but they don't appear, they are not consumed. We're able to recover them back when we finish the reaction. So next question I've gotten asked, can you go over number 3 in the pre-exponential factors in EA homework? I'm I'm guessing this is one of the ones I need the Excel sheet for. Yep. So give me just a minute to bring up the Excel sheet. Now for finding the EA, we're going to use the Arrhenius relationship. So in your rate law, we have R equals K times concentrations raised to a power. And what we're looking for is a way to describe this factor K, the probability they will react, and we do this using transition state theory. So transition state theory says that K equals some pre-exponential factor times e to the minus EA over RT. Now, the term pre-exponential factor just means it's the factor that appears before the exponential, so that's why we call it the pre-exponential. The EA here is reaction specific. So it's looking at the energy required for a specific reaction following a specific mechanism. So it is unique to a reaction. The pre-exponential factor is not. The pre-exponential factor contains some reaction-specific information, but it also contains a lot of things like unit conversions. It contains a lot of information about how the reactor is designed. So in practice, the EA is the more important number, but we can still extract out the pre-exponential factor for our reactor. To do this, we need to linearize. So we're going to linearize it the same way we linearize the first order reaction. We're going to use a natural log. So we get ln of K equals the ln of A minus EA over R times 1 over T. So that natural log is going to bring this down, and we get this relationship. We're given K, so our ln of K is going to be our Y, and we're given temperature, so our 1 over temperature here is going to be our X. Now, a few comments on this. R here is the ideal gas constant, and we're going to focus on R being 0.008314 kilojoules per mole Kelvin. We report in kilojoules because that's what all thermodynamic parameters are reported. They're so big that we have to practically work with kilojoules. Now, because R is in per moles Kelvin, temperature here also has to be in Kelvin. So in terms of how you actually do the analysis, give me my desktop, and we'll go to case 3. You need your X and your Y values. X here is going to be 1 over temperature. So if you do equals 1 divided by, the temperature has to be, you see the temperature with the C mark here. We're going to add 273. Our Y value is the ln of K, or the ln of the rate constant. So now we have our X and our Y, and we just need to make a plot. Again, we're going to do a scatter. We're going to add a trend line. Make this bigger. It's at least somewhat visible on your side. So right above this, I'm going to put the Arrhenius equation. So we have ln of K equals minus EA over R times 1 over T plus the ln of our pre-exponential factor. So These are lined up side by side with the final plot. We generated the ln of k, so we created that y value. And we plot it 1 over t, which is our x value, so that tells us that this minus EA over R equals minus 6721. And similarly, our ln of A is equal to 6.6587. So these are the parallels we're going to draw between our theory, the ln of k and the Arrhenius relationship, and what we actually got in terms of our numbers. So now if we just solve for it, EA just minus R times minus 6721, you will get a number. A here is e to the 6.6587. Now, just to kind of help you out, and like I'm not making this up, these are real things, EA is typically between 25 and 150 kilojoules per moles. It can be outside that range. Generally speaking, though, most of life operates in that range. So if you're getting 25 to 150, your answer's probably right. There are reactions that are above and below that range, but most of life operates in that range. In terms of the pre-exponential factor, it's all over the place because you see that your rate constant there is in per minutes. If you were to switch that to per seconds or per decades, it would radically shift what the pre-exponential factor was. Now, that said, for WebAssign, it's meant to be a pretty straightforward number, so you don't have to worry about entering in exponentials. So for the third one, the A here to 3 sig figs is 781, and the EA here to 3 sig figs is 55.9. But yeah, for WebAssign, I intentionally cooked the numbers so that it would give you something that you could enter in without having to use like weird exponentials. Yeah, but if you look at the practice packets, they're all over the place because those are not meant to be turned in. So you can take a bigger range. Yeah, but you're very welcome. All right, other questions? Go ahead and wipe this down. Now, someone did send me an email saying that I think the book was telling them to do like the natural log of k1 minus k2 over divided by 1 over t1 minus t1, 2. Do not do that. To be honest with you, you're going to find throughout your education there are people who write textbooks who have absolutely no background with what they're writing a textbook on. This is one of those cases where someone wrote a textbook. No one does that. There's a lot of good reasons for that. One is that it's statistically meaningless to take 2 data points because there's error associated with them. When you take a quantitative chemistry course at a higher division, you actually go through how to do statistical analysis in Excel, and it will tell you the uncertainty on your activation barriers and the uncertainties on your exponential factors. So off the bat, what the book's recommending doesn't give you anything statistically meaningful. The second is that an Arrhenius plot tells you a lot about reactions. So this actually came up with work I was doing at Stanford, where we would watch the Arrhenius plots do this. So we had ln of k, 1 over t, and it looked like there were two lines. Well, this is the point where the rate limiting step changed. So the mechanism itself took on a different form. You don't know that working with just a 2-point analysis. You just kind of have to assume that between those 2 points you're getting meaningful information. So again, you're going to find this with books every now and then, particularly with the electrochem section this semester. You're going to find it's not done by someone who really knows a lot about the field. Don't do the 2 points. Do the Arrhenius plots. This is actually considered like really basic analysis. There's Eyring plots. There's way better ways of doing it than what we're doing. This is just kind of a nice intro on how to do this type of analysis. But don't do a 2-point analysis. It's statistically meaningless. Those of you who are still waiting on your lab kits, yeah, we understand. We finally got an email back from Carolina Biological saying that they kind of ran out of peroxide and ran out of vinegar, so they're waiting to ship out your kits until they get a hold of them. Just keep me posted on how many extensions you need. The goal here is to get you to do the labs. It's not, I mean, unfortunately, you're going to get backlogged with 4 to 6 labs you're going to need to do, but the goal here is not to penalize you for not having the lab kits. The goal is to make sure that you do the labs. If you need the extension, you need the extension. As far as the tutorial quiz goes, go ahead and take it. You don't need it for the labs. It's more just kind of making sure you understand how to keep a lab notebook and how you give an oral presentation. That's why it's due tomorrow, is more for the next 2 weeks you'll be writing your oral presentations and getting ready to give your oral presentations to make sure you have a feel about what you need to be doing. But the tutorial quiz is not going to have an impact on, is not based on any labs. It's just more meant to make sure that you understand the written and oral components of the lab. But yeah, to complete the tutorial quiz, it probably takes you like 5 or 10 minutes. You're welcome. Again, with the labs, I want you to do them. If you have to do them 2 weeks from now, you have to do them 2 weeks from now, but I would rather you do them than not. So when you do them is not so important. I hate to say that to people who've already done it or doing labs. Those of you who've done labs and are doing them because you had the lab kits, just understand that the people who don't have the lab kits are going to have to do a whole bunch of labs. You're going to basically double time a lot of labs. So yeah, you did it early, you didn't have to do it early, but on the other hand, you don't have the stress of doing a whole bunch of labs at once. The goal here is to get you to do the labs to reinforce the concepts we're talking about in the course. This supplier issue is completely outside your control for those of you who haven't gotten the kit. So again, I would rather you take like 4 weeks of extensions and get the labs done than you get penalized or do a lab that's not particularly useful, like a paper lab, in its place. Other questions? Let's see what your discussion board is for tomorrow. Oh, method initial rates. That one's going to be real easy. Also remember that your second exam is next week. You have from Monday, I believe, through Friday to take it. Start it early. It's not a particularly hard exam. It's very easy relative to what the homeworks are, but it's also kind of merciless in that the answers are pretty binary. You got it right or you got it wrong. But as with all exams, don't ask about your grade until I've had time to grade it. Yeah, Blackboard gets the grading wrong all the time. When you see a 1 out of 1 on your work, the work that you submit, that's when you'll know I've gone through and graded your exam. So wait until you see that 1 out of 1. You're probably going to see your grades improve like 40 or 50 points if you did them right. It's WebAdvisor. It doesn't understand free response. I can try to program in algorithms, but ultimately I have to go through and grade them myself. So again, exams are next week. You have the full week to take it. I'd say go ahead and knock it out early and get started on the kinetics. Test 3 is going to be the hardest exam for you simply because it spans a lot of information. A lot of it is stuff that it's much more abstract and it's probably not what you're used to working with in terms of chemistry. It's also very algebra heavy. So let's give it another 5 minutes. If people have more questions, we'll just sign off for the day. And if you need lab extensions, send me emails. What I do is I'm just going to do them all tomorrow since I need to go through and grade a whole bunch of stuff tomorrow anyway. I'm just going to keep a list of emails and go through and just go ahead and do the submissions. If you see by like Thursday night I haven't given you an extension, and you or let's say Friday you see I haven't given you an extension, you say, hey, I forgot to send the extension. That's fine. Just let me know. Things do get buried in the minutia. Again, thing is you just getting the labs done. So if you need an extension and you aren't able to get to me before Friday, that's fine. Just send me an email saying you need a submission. The emails are mostly so I know who has a kit and who doesn't. All right, we're gonna give it about one more minute. All right, so not seeing any more questions. As always, if you have questions, email them to me or send me a chat through Teams. If you're not able to make a live stream, send me an email and I will try to make sure that whatever question you send, I address at the start of the live stream. So when you see the live stream or you go look at the live stream, your question's answered pretty quickly. Again, don't forget you got your test next week. I will see y'all tomorrow, hopefully. Thanks for showing up.